Hello, welcome to our presentation on our project of impact of undersampling the case-space data and solutions for minimizing artifacts due to undersampling in MRI images. This project is part of our Bilkent University EE 473 medical imaging course. My name is Oyku Ozbirinci, and I collaborated with Ozdilek under the guidance of Associate Professor Ihsan. And today we'll be discussing how case-space undersampling impacts MRI image quality and certain methods to address these challenges. To give a brief introduction to the topic, MRI is a widely used non-invasive imaging method, and it leverages the magnetization of hydrogen spins. The process involves sampling the case space, that is a frequency domain representation of the MRI image. However, according to the Nyquist theorem, full case space sampling is necessary to avoid artifacts, and this creates a challenge because full sampling can be very time intensive. And our project focuses on understanding the trade-offs between undersampling and minimizing the resulting artifacts from undersampling. Our goal in this research is to address the artifacts and aliasing that occur due to case-space undersampling, and we aim to evaluate the efficiency of various undersampling techniques. We evaluated the efficiency of 8 undersampling techniques and determined their impact on diagnostic accuracy while improving the acquisition speed in MRI imaging. We used 8 undersampling techniques in this project. First one is random sampling. The random sampling technique samples half of the case space data, approximately 50% randomly. The second technique is variable density, which prioritizes low frequency sampling. The third one is variable density technique combined with partial Fourier. And this combines the probability-based sampling with the property of symmetry. And the fourth technique is uniform undersampling, which samples exactly 50% of the case space data at regular intervals. The fifth one is center-weighted undersampling, which focuses on the low frequency case space regions. And the sixth one is radial undersampling, which scans the polar coordinates for motion artifact mitigation. And the seventh one is partial Fourier technique, which utilizes symmetry in the domain to half the required sample in the case space. And the eighth technique is Cartesian, which uses directional resolution prioritization. And we used, for example, the y-axis, but it could be applied to the x-axis as well. These are some of our results from the masks of the undersampling techniques. The uniform undersampler samples 50% of the data at regular intervals, whereas random undersampling, for example, samples at random intervals, about 50% of the case space. And I also briefly went over the other samples. Efe will be talking about the other methodology.
Compressed sensing is a technique that exploits the sparsity of a signal in the frequency, image, or wavelength domain. And the main objective of the compressed sensing is to employ an iterative approach to reconstruct the image from fewer samples required below the Nyquist rate. And we use two compressed sensing techniques in our study. One of them is wavelet regularization. In the wavelet regularization, main objective is to encourage sparsity in the wavelet domain. You can see it from equation 6 as well. And we need to minimize the L1 norm of the wavelet transform of the image. For total variation denoising, we need to have sparsity in the total variation, total change of the signal in the image domain. And we need to minimize the L1 norm of the total variation of the image as well, similar to the equation 6. For this study, we used 2 main data sets, and one of them is the data set from BrainWeb, McGill University. It's a simulated data set, and it has different imaging modalities, and we can adjust noise levels, slice thickness, and also RF homogeneity. And we also use the R35H brain tumor detection data set. It mainly includes tumorous brain MRIs, and we used it to distinguish the tumor in a brain without undersampling and with undersampling in order to see the accuracy of the undersampling methods.
And here are results for our evaluation. This is from the T2 modality technique BrainWeb dataset from McGill University. Among the techniques employed in this modality, the partial Fourier method performed the best, and it gave almost perfect results for the recovery of real images. And the combination of variable density and partial Fourier also produced very high quality results, while only using 25% of the case space samples. Additionally, the center-weighted sampling effectively preserved the structure of the image. However, techniques such as the uniform and random undersampling showed very significant limitations, and this was particularly due to the poor low-frequency sampling in the random undersampling technique and aliasing that happened in the uniform undersampling technique. And here are some other results from the other data set that we used, and this is from the tumor detection data set, and the results are very similar to the T2 modality results. This is another sample from the same data set. To evaluate the performance, in summary, the best performers were the partial Fourier method with almost perfect recovery for the real images. The variable density plus partial Fourier method combination also gave excellent quality images with only 25% sampling of the case space. And the center weighted also was a good technique to use for structural preservation. The radial Cartesian and variable density techniques were moderate performers, and it was decided that the radial undersampling technique was much more effective for motion compensation in motion artifacts and not for our case in our research. The Cartesian technique gave good directional resolution, and the variable density technique gave moderate performance. And the uniform and random undersampling techniques were quite poor performers because the uniform undersampling technique gave significant aliasing artifacts, and the random undersampling technique was inadequate for low frequency region sampling. Now for our results in the pathology detection. When we use the tumor detection datasets, tumor visibility maintained in most of the methods, and there was very clear tumor distinction in partial Fourier method. There was good soft tissue contrast and preservation in most methods. However, some methods do require additional processing, which Efe will talk about now.
For random undersampling, we need to utilize several compressed sensing techniques, as I mentioned before. For instance, we need to use total variation regularization for the randomly undersampled image. And as you can see from our figure, it increases the soft tissue contrast, and it also increases the resolution. And in the left, the tumor is indistinguishable. However, we can differentiate it from the image in the right side. And again, now we are using wavelet sparsity regularization. Here also you can see that the soft tissue is invisible in the randomly undersampled image. But when we use wavelet sparsity regularization, we can easily distinguish the soft tissue from the background. Compressed sensing worked accurately for the randomly undersampled image. Wavelet regularization improved the soft tissue contrast, and we can identify the pathological tumors more accurately. And for total variation denoising, the blur was cancelled with an iterative algorithm using gradient descent algorithm, and we can and we could enhance the tumor visibility as well. And here you can see the adjustments that we have made for the uniformly undersampled image. Firstly, when we uniformly undersample the image without pre-filtering, there occurred aliasing. And in the second image of this figure, you can see that nothing is distinguishable. However, with an anti-aliasing pre-filtering prior to the undersampling operation, we can easily distinguish the tumor from the background. And in the last image, a low-pass filter in the spatial domain was implemented in order to see the tumor's brain tissue. And therefore, for uniformly undersampled images, we can use anti-aliasing filters, and this improves the soft tissue contrast and resolution dramatically. And also, we can identify pathological tumors as well, as I mentioned before. However, we lost some of the details at the edge of the image in order to avoid aliasing. In conclusion, we can minimize the artifacts using several undersampling schemes, such as the variable density undersampling or in the partial Fourier method for real images. However, we lose in resolution and contrast in trade-off between the scanning time. And for randomly undersampled and uniformly undersampled images, we can use several techniques such as compressed sensing or the anti-aliasing filter. And overall, the low frequency preservation is crucial, since low frequency regions are the main low frequency regions are mainly responsible for the whole image, and high frequency regions are responsible for the details of the image. And also for several tumors or several patients, directional imaging can be significant. Therefore, we can use Cartesian undersampling, and it can be advantageous for diagnosing several diseases.
We also shared the reconstruction methods and undersampling methods on a GitHub repository in the given link, and the database references and the references to the generative AI models that we utilize in the project are also presented in the references. Thank you for dedicating the time to listen to our presentation.
Now we will be performing a brief demo. We have 3 samples here,
Two of them are from the tumor detection dataset, and the other is from the T2 modality brain web McGill's dataset. Now, when we run the main code, we have all three of the samples included in the script, and each of the samples are undersampled with 8 different techniques, and the masks for each of the 8 techniques are printed on separate figures. And then after each sample's undersampling methods are tried one by one, all of them are printed on a larger plot. Now, firstly, this is the T2 modality image undersampling techniques, and it's followed by one of the samples from the tumor detection dataset, and the tumor's visibility is seen clearly here. And here's the other sample from the tumor detection dataset. This is the end of the demo.